Hello, my name is Marvin, Ogore, and I'll be presenting on offline prediction of cholera in rural communal tap waters using HAI inference. The team is consisting of myself, Marvin Ogore, Dr. Jimin Senga, and Dr. Kizito. We're coming to you from the African Center of Excellence in Internet of Things, which is part of the University of Rwanda, which is funded by the World Bank. So I'll go right into my presentation. So the motivation of this study was based on the societal challenge of the cholera disease burden. So we noticed that Africa accounts for 54% of the disease burden in the whole world. So it's a global pandemic, and Africa accounts for over half of it. Cholera is a waterborne disease that causes up to 200,000 deaths yearly. So this was a motivation for our study. Also, existing detection technology for cholera is not cost effective. That means that it's very costly and it's very expensive, which means that it cannot be scaled to mass deployment. So we were targeting rural water taps. So we looked at how cost might affect the deployment on all rural taps, that is mass deployment. Conventional detection techniques take up to 24 hours and require lab setting. So an example is in the alkaline peptone water, which is a lab reagent that requires you to have, it takes up to 24 hours for you to get the results to know whether cholera is actually in the water or not. So our research basis is based on communal rural water taps, as I mentioned, in sub-Saharan African rural settings. We decided to use HAI because of poor rural internet connectivity, so that does away with internet connection in IoT settings. So IoT requires you to have sensor data sent to the cloud frequently, so that will be a challenge in rural settings. So it would be useful to have HAI, so detection in our so that we can have fast response, and also for mass deployment. So the solution will be cheaper compared to conventional cholera detection techniques. So for our HAI situation, we'll be using data that consists of physical chemical parameters of water, which I'll describe later as we go on through the slides. So state of the art, we'll notice that current methods being used, that you are using technology, try to miniaturize the lab setting. So we have lamp on a chip. We also have a sensor node that are monitoring diseases causing bacteria like E. coli. They require lab reagents that are expensive and constantly need to be refilled. Some situations use even an iPhone, which is not practical for the sub-Saharan setting. This is a device that is power consumption. We notice that TinyML is targeting devices that reduce the power consumption, and also lenses that are being used to magnify the detection of cells is quite expensive. So we look at an ML as a solution to this, removing the human expertise and removing also the need for labs. So this will fill also the gaps that were identified in this situation. The solution will be a pluggable device, the communal rural taps, sensing data, sensing physical chemical parameters of water, temperature, turbidity, pH, conductivity, which is also related to salinity. So these are the parameters that are necessary for existence of biological matter in water. This affects the existence of cholera cells, the number of cells. They will determine how many cholera cells will be in water, and how they will determine whether they will increase or reduce. Also, so these sensors will be able to digitize water and fed into an MCU that is ARM-based. That one will onboard our machine learning via TinyML, and we'll be able to send notifications via GSM. Since internet connectivity is an issue, we should have a structure. So GSM is a robust existing structure that can be used to leverage on the notification of health officials. We'll also have LEDs that will indicate whether water is safe, whether water is unsafe, and also we'll be able to narrow down on the specificity of detection of a specific waterborne disease, in which case this scenario we are looking at cholera. Moving on, we will start with the original data world set, which is based on Lake Kivu, which is at the border of Rwanda and Congo, as shown in the map of Katana Health Zone. So the study we got this data from contained physical chemical characteristics of Lake Kivu, that is temperature and salinity, collected against the concentration of Vibrio cholerae, that is the scientific name for cholera, found in lake water. So they were looking at how salinity and temperature affects the existence of cholera in water. So we chose data that is closer to home. So since we are basing our research on African settings, we found the more robust data that has existed was from this study that was carried out from Katana Health Zone. So the data was collected twice a month over a period of 48 sample weeks over the 2016 to 2017, consisting of 289 observations. We will notice that this is not sufficient data in terms of volume and size. We need a large data set, and the approaches to this would be using appropriate machine learning algorithms for low data sets, and also exploration of generation of synthetic data sets. Moving forward, our HAI prototyping tool stack, so TinyML, can be replaced for HAI. They can be interchanged as you see fit. We started with the original real-world dataset as described in the previous slide, and since it was a low data set in terms of volume and size, we decided to use synthetic data generation, that is mostly generate a tool that can be used to learn the patterns of the existing data and try and replicate the patterns, not really duplicate the values, but really try and learn the patterns from each class and see how the data trends are occurring in each class and try to replicate that kind of pattern. Also, so after that, we split the data into training and validation sets. So the training data consists of validation and training sets, where we would be able to learn from that pattern and see how we can be able to detect cholera and no cholera. So we divided it into two classes, no cholera and yes cholera. Also, we split the data into a test and validation set, and we also split into a test data set that will be consisting of real world data set. So Edge AI as a service, we were using Edge Impulse as our tool stack in order to learn from the data and to be able to classify it into yes or no cholera. So yes cholera or no cholera are our two classes. From there, Edge Impulse provides us a way to download a CMSIS pack for STM32. That is a library that can be downloaded. That is a model that has been converted into a library, and we can use our Edge AI application IDE STM32 that will be able to help us get a hex file that can be used on a Proteus embedded simulator. So this simulator, we will be feeding it test data and inferencing our results on yes or no cholera. So during our training, we compared two machine learning algorithms, that is the Edge Impulse native neural network and a quasi SVM in Keras. We got it from the documentation. You'll notice that there's difference in the layers and the number of neurons. So SVM was seen fit to be performing very well when performing water quality analysis in detection of quality of water, whether it is safe or unsafe for drinking. In terms of, so it was a general outlook on how its effects on pollution and such. So they never narrowed down on a specific detection of public health scenarios like waterborne disease detection. So that is why our research is more interesting in that aspect. So in a comparison of the two, you notice that Edge Impulse had a 90% accuracy, while Aquasi SVM had a 94% accuracy. The difference in the two also is being showcased with the loss that is being used, where Aquasi SVM in Keras is using a squared hinge loss. So what we also notice is that the Edge Impulse native neural network required a lot of manipulation in terms of parameters, adjusting the learning rate in order to achieve higher accuracies and also to reduce the aspects of overfitting, whereas the Quasi SVM performed quite better as compared to in terms of trying to adjust parameters, time consumption taken during the adjusting. SVM performs quite better. So it was noted to be a suitable machine learning algorithm when it comes to low data sets. So the embedded simulation started from when we finished our training, we were able to download our CMSIS STM Cube library pack that we use on the STM Cube IDE in order to get a hex file that we can deploy on a Proteus system simulation. So the PCB layout is simulating an actual board. That is, the target board will be consisting of an MCU that has ARM Cortex M4 core with DSP and FPU, 512 kilobytes of flash memory with 884 megahertz of CPU. So we also have an LCD and a virtual terminal in order to see our outputs, whether the classification is working correctly or not. So the embedded simulation results, we noticed that we compared the live classification to the Proteus simulation, and what we noticed is the comparison shows that the Edge AI model achieves similar inference accuracies when running on embedded processors as well as on the cloud. You'll notice that we have an accuracy of 88% and 88%, while classification is 89%. So this varying is almost negligible, of almost 1%, and we will attest this to processing power provided from the cloud and also in comparison to the simulation embedded simulator. So the hardware performance as well is as shown on the diagram. We noticed that we had enough memory space in order to actually store our program in a dynamic memory, as well as also leaving space for bytes for local variables. And the maximum is 262 144 bytes. We noticed that it also takes 1 microsecond for classification, which was very good speeds. Also, we used different features, and we also noticed that the classification matches the one on the cloud. So on the embedded hardware performance, was also the results that were acquired were desirable. On the real-time embedded processor specifications are from Edge Impulse. We had a 94% accuracy model inference performance. We had a comparison with SVM and native neural network as mentioned previously. SVM had 94%, native neural network had 90%. And the on-device real-time performance, you'll notice it's 1 microsecond inference time, and the RAM and ROM estimates as follows, as shown on the diagram, of 1.5 kilobytes, while the ROM is 14.9 kilobytes. So in the conclusion, We set up a prototype stack integrating Edge Impulse, STM32Cube, and Proteus. The inference on virtual embedded platform is similar to the one obtained on the validating in the cloud. A shallow machine learning is suitable for small datasets, namely SVM, and the synthetic data generation to artificially increase the original dataset is used. The accuracy has been 94% for SVM and 90% for the neural network for synthetic data on test data. Future works will be involving prototyping on a real embedded development board, as we had started with Arduino BLE. So we were also scaling from STM Cube to other embedded providers such as Arduino. We also need to compare lab control comparisons, that is using a non-contaminable variant of Cholera in order to compare how TinyML compares to laboratory settings. We also need to explore more datasets for different sensor fusions that will be enable us to have a more insight and also improve on the model that we currently have. This study was able to attract various stakeholders such as TinyML. We were able to be selected as the best abstract in the TinyML EMEA annual meetup that occurred in June. Also, were invited as guest speakers for the RSIF guest webinar series, and this paper has been accepted into the IEEE GlobeCom, which is a CC Sessions workshop, which is scheduled for 7th to 11th December 2021 in Madrid, Spain, which will be a hybrid in-person and virtual